Hello friends, I welcome you in lecture number 33 on relations. In lecture number 31, we have discussed about equivalence relation, and using equivalence relation we are going to talk about equivalence class in this relation. We know that equivalence relation is a relation which is reflexive, symmetric and transitive. So suppose R is an equivalence relation on a set X, that is R is a subset of X cross X which is reflexive, symmetric and transitive. Then we can define equivalence class for every element of given set X. Suppose I consider small x in a set capital X, then if I collect all those elements of set X such that X is related to those elements, then this set is nothing but subset of given set X, and it is the collection of all those elements in set X such that this X is related to Y. We can write in this way also. We are considering all those elements Y in X such that ordered pair XY belongs to relation R, where R is an equivalence relation on a set X. So this set is the set of relatives of X in a given set X, and this set is called equivalence class generated by this element X, and it is denoted by this notation. And here we can write capital R to specify that we are using this R equivalence relation, or we can simply write equivalence class of X in this way also. So for every element of a given set X, we can write equivalence class generated by that element, and it is the collection of all those elements of given set X which are related to given element X. So we can see that equivalence class is generated by each element of given set X are nothing but subsets of given set X. So this is the definition of equivalence class. Let R be an equivalence relation on a set X. For small x in a capital X, the subset of capital X given by all those elements Y of X such that X related to Y is called an R equivalence class, or simply equivalence class generated by small x belongs to capital X, or we can say that this set is an equivalence class of small x, and this is the notation for equivalence class. We can use this or this notation, and equivalence class of X consists of all the R relatives of X in the set X. The relatives of X in the set X constitute an equivalence class generated by that element X. The equivalence class generated by X can also be written as this symbol X quotient R. And here I consider this example to explain the equivalence classes generated by elements of a given set. We have taken capital X equal to 1, 2, 3, 4, and here R is a relation on set X, that is R is a subset of X cross X. So we are considering some ordered pairs of X cross X, and we have written this relation on set X. Now you can prove that this relation R is an equivalence relation on X. You have to show that R is reflexive, symmetric and transitive. And here we are going to find equivalence classes generated by each element of given set X. So first element is 1. So first we find out equivalence class generated by 1. Now by definition of equivalence class, I have to write down all those members of a given set X which are related to this 1, that is 1 is related to Y, or I have to write down all those elements of set X such that ordered pair 1 comma Y belongs to R. Now I have to concentrate on those ordered pairs whose first component is 1 in the given relation and their second component will be member of this equivalence class. Y belongs to X such that ordered pair 1 comma Y belongs to R. So we will concentrate on those ordered pairs whose first element is 1, and for that ordered pair we will write down second component which is Y for this equivalence class. So here we mark all those ordered pairs whose first component is 1. So there are only two ordered pairs having their first component as 1 and their elements second components are 1 and 4. So here I have to write 1 and 4. So we can say that 1 and 4 are related to 1. Here 1 is related to 1. Therefore 1 is in the equivalence class and 1 is related to 4. Therefore 4 is also in equivalence class. We are considering all those elements in the equivalence class which are related to 1. So we find that 1 is related to 1 and 1 is related to 4. Therefore 4 is in this equivalence class. And there is no other element whose first component is 1. So we are having only two elements in the equivalence class of 1. Now we find out equivalence class of 2. So I have to write down all those elements of X such that 2 is related to that element. So this I can rewrite as Y belongs to X such that order pair 2 comma Y belongs to R. So now I have to concentrate on those ordered pairs whose first component is 2. So let me see this relation and I have to search for that ordered pair whose first component is 2, and there are two ordered pairs having first components as 2. So for this ordered pair we can say that 2 is related to 2 and here 2 is related to 3. Therefore relatives of 2 are 2 and 3. So here I have to write 2 and 3. This is the equivalence class generated by element 2. Now we find out equivalence classes generated by 3. So now we consider Y belongs to X such that 3 is related to Y, and therefore Y belongs to X such that ordered pair 3 comma Y belongs to R. And now we have to concentrate on those ordered pairs having first component as 3. So here I have this ordered pair having first component as 3 and this also. For this ordered pair we can say that 3 is related to 2, and for this ordered pair we see that 3 is related to 3. Therefore relatives of 3 are 2 and 3, or we can write these second components 2 and 3 in the equivalence class. So here I write 2 and 3 and we find that equivalence classes generated by 2 and 3 are same. Now similarly we can find out equivalence class generated by 4. So Y belongs to X such that we can directly write now ordered pair 4 comma Y belongs to R, that is 4 is related to Y. Now I have to concentrate on those ordered pairs having first component as 4, and we find out these two ordered pairs whose first components are 4 and second components are 1 and 4. So here I have 1 and 4. So this is the equivalence class generated by 4 and it is same as equivalence class generated by this 1. So we can see we have equivalence classes generated by 1 and 4 are equal, and they are having two elements 1 and 4, and equivalence classes generated by 2 and 3 are equal, and their elements are 2 and 3. Let me verify again. This is fine, 2 and 3. So we can see there are two distinct equivalence classes 1 4 and 2 3, and equivalence classes generated by 1 and 4 are equal, equivalence classes generated by 2 and 3 are equal. So now you can observe these properties, some properties of equivalence classes, that here equivalence class generated by 1 contains 1 and 4, and we have 1 and 4 in this equivalence class. That means 1 is related to 1 and 1 is related to 4, and we can observe that 1 is related to 4 and equivalence class generated by 1 and 4 are same. Similarly, we can see that 2 and 3 are related. We can see that ordered pair 2 3 belongs to R, that is 2 is related to 3. Here we can observe that 2 3 belongs to R, that is 2 is related to 3, and here we observe that equivalence classes generated by 2 and 3 are equal. So from this we can see that if two elements are related to each other, if X and Y are related, then equivalence classes generated by X and Y are always equal, and converse is also true. We are not going for the proof of this result, but this is always true for any two elements which are related. If two elements are related to each other via relation R, then equivalence classes generated by those two elements are always equal. This is the first property which we have observed using this example. Another property you can see is that equivalence class generated by 1 contains 1, equivalence class generated by 2 contains 2. Similarly, equivalence class generated by 3 contains 3, and equivalence class generated by 4 contains 4. So from this we can write or observe another property of equivalence class, that is equivalence class generated by X always contains that element X. X belongs to equivalence class generated by X, and we can see that here I have 1 2 3 and 4, and equivalence classes generated by these elements are 1 4 and 2 3, and if we take their intersection, suppose equivalence class generated by 1 and 2, if we take intersection of these two, then we have empty set. Similarly, we can take intersection of equivalence classes generated by 3 and 4 is also empty set, and equivalence classes generated by 1 and 4 are equal, and 2 and 3 are equal. So what we can observe from this is, if we take any two equivalence classes, then either they are equal, that is equivalence class generated by X and equivalence class generated by Y are equal, or disjoint, that is their intersection is empty set. Equivalence classes generated by two elements are either equal or disjoint. We cannot say that this intersection contains two elements or three elements. Either these two sets are equal or their intersection is empty set, that is they are disjoint. So that is the another property, that equivalence classes, two equivalence classes are either equal or disjoint, or equivalence VALENCE, equivalence classes generated by two elements or two equivalence classes are either equal or disjoint. And two equivalence classes are equal if and only if these two elements are related. If x and y are related, then only equivalence classes of x and y are equal. If x and y are not equal, not related, suppose x is not related to y, in that case we will have disjoint equivalence classes, and that we observe here also. Here equivalence classes generated by 1 and 2 are different, and we can see that this ordered pair 1 2 is not present in our relation. You can see order pair 1 2 is not present. Similarly, order pair 4 3 is also not present. 3 and 4 are not related. Therefore, equivalence classes generated by 3 and 4 are disjoint. So this is all about equivalence classes. Here I have written some properties which we just discussed. Properties of equivalence classes. Let capital R be an equivalence relation on a set X. Then for any X in the given set X, X is always member of equivalence class generated by X. If two elements are related, then their equivalence classes are equal, and if equivalence classes are equal, then two elements are related. Equivalence classes generated by any two elements are either equal or disjoint. One more thing which we can observe from this example is that if we take the union of disjoint equivalence classes, here we have two disjoint equivalence classes. So suppose I consider union of two disjoint equivalence classes, then we can see we have 1 2 3 and 4, that is capital X. So union of these two sets is equal to capital X, and these two sets are disjoint. Therefore we have partition of this set X, and that partition has blocks as equivalence classes. So this is a partition of given set X. Equivalence classes always gives us a partition of given set X because their union is equal to given set X and they are disjoint. So that is one important remark. They can ask you to write down the partition of given set X using equivalence classes. The collection of all equivalence classes is a partition of the set X. The blocks of this partition are equivalence classes generated by elements of X. So as in the case of example which we just discussed, we find that equivalence classes generated by 1 and 4 are equal, and they contain two elements 1 4, and similarly equivalence classes generated by 2 and 3 are also equal, and they have two elements 2 and 3. So we have this partition equivalence class generated by 2, and we can write 4 also. Okay, we have to write two disjoint equivalence classes. Either we can write 1 or 4 or 2 or 3. So this is a partition of given set X because union of these two sets is equal to capital X, and these two sets are disjoint. And here we can see this is nothing but equivalence class of 3, and this is equivalence class of 1. So if we consider disjoint equivalence classes, then their union is always a given set X, and therefore this collection of disjoint equivalence classes is always a partition of a given set X. So using equivalence relation, we can find out the partition of a given set X whose members are equivalence classes. Equivalence classes gives us the partition of a given set X. So they can ask you to find out the partition of a given set X corresponding to given equivalence relation on a given set X. So this is all about equivalence classes, and we will continue with equivalence classes in upcoming lectures also. Thanks for watching.